his presentation will answer a lot of questions that were posed to previous two speakers. So he probably will give credit to Aaron and to London.
Aaron and Landon.
Yeah, but this teamwork goes out of box. It goes out of restriction of one dimension and shows some details about charge transfer in like multi-dimensional charge transfer. Okay, let's go ahead.
So we are looking at generating 2D dynamics in space. So to begin with, we need our input files. So all these files on right here are the input files we need for the MATLAB code. And then we have a few different files we need to generate them. So we need par charge files and the trim.sh code. And that code generates the par charge.trim files and the lockpot.trim file. And then we need our concar and the atom.sh code, and that's going to generate these xx1.xyz files. In addition to that, we also need the RRR, the band out, the energy pop, which are the standard that we've been discussing for the last few weeks. And then these two MATLAB codes, and then the band out 2D, which is generated by this first MATLAB code. So if we look at how we actually generate these, so here we're generating the .trim files. So if we look at the .trim script, so you would want to copy the par charge files into a separate directory because the script deletes them at the end. So what the script does is it takes the par charge files and converts them into a form that MATLAB can read. So the things to look for here in the red box here, you want your orbital indexes. And in the blue box here is the number of lines to delete from the par charge file, which should be your atom count plus 9. So when you run the script, it'll give you this string here telling you that it's working. So then if you open one of the .trim files, this is what it should look like. So you start out with this line with 3 numbers. Those are grid points that we're going to use. And then everything after that is the orbital data for that band. So if you were to open just the plain par charge, you would see a copy of the postcard above this. That's what we deleted with the script on the previous slide. And then to create the XYZ files that we need to first create a postcard.xyz, which I have detailed how you can do on NERSC. So if you type in module show paths, it'll give you a list of useful paths, and you're interested in this one that has the VTST scripts in it, and then you can, using that in that directory, there's a postcard to XYZ script that we can use to create the postcard.xyz file. And then you can run the atom.sh script, and it will request that you enter in the atoms in your model. So enter those in, and then it will make XYZ files for each atom. So then if we look at our first of the MATLAB script, which is the trim parts 2 x.m, and there's a few different versions where there's different letters instead of x. There's a y, there's an a. So this file needs all the .trim files that were generated by the trim.sh script. So you're going to need all the par charge.trims and the lockpot.trim. And all the lockpot.trim is a copy of one of the par charge to get the initial dimensions. So some things you need to some things you need to work on or modify. You have your HOMIN, and OMAX like normal. Depending on what band you're looking at, you may have to change the number of zeros here in the bar charge, and you will have to modify the several of these lines. This first, the Z equals, the Y equals, the band out equals, the orbital equals, and the index 3, depending on which dimension you're trying to integrate over. And you would have to make the same modifications to this for loop, which is a little farther down. So in this case, we're integrating over the X dimension. And this script will pump out a figure that looks something like this. Now for the second script, which is the another one of these 4 MEQ scripts, you see that we have our standard parameters, the IH, the IE, HOMO, OMIN, OMAX. So you need to enter all those. Then a little further down, you'll find this band out 2D equals load line, and you'll see all these dim1, dim2, dim3. You need to enter those values, and they are those. They are these 3 numbers right here. And another way you can look at them, this is from the workspace on MATLAB from the trim.m script, so it reads it in there as well. Another place you need to change is this line, which is toward the end of a really long for loop. This is what gives you the axis you're interested in. So you can see that I've matched it up to dimension 1 and dimension 3. Because I'm looking at the XZ plane. So then we need to load in our atom coordinate files. So this is all the .xyz's that we generated. So you see in here, we have them where they load and we're loading, and you notice that they all are a atom symbol 1.xyz. So chlorine, carbon, cesium, hydrogen, nitrogen, lead. Another thing to note with where these red boxes are, depending on what plane you're looking at, you will have to change those numbers.
David, where did you generate those XYZ files?
Right here. So we use this atom script to base them.
Oh, okay, sorry. Good.
So you just this requires our postcard.xyz as an input, and then you adjust when it requests it. You enter in what atoms are in your system.
Yeah,
and
gotcha.
it'll go through and make all the XYZ files we need for that step.
Okay, thank you.
So then further down the line, we need to specify bonds, and you need to do this for every bond type that you're interested in. So I've opened up the for loop for the carbon-hydrogen bond so you can see it, but there's also nitrogen, hydrogen, carbon-carbon, chlorine, lead, any bond type that you're interested in, you would have to do this for. So the major thing here is, once again, depending on what dimensions you're looking at, you would have to change the order of the Z, Y, and X in this box. So here we need to specify the number of states for the conduction band and valence band. So you see we have these numbers right here to specify that. And then you click run and hope that it works. The code takes a long time to run. So if you if it works somewhat, it needs to be cleaned up. You get a picture of what we're seeing off to the left, but not to the right here. And you can see that we have a contour graph overlaid with my atomic system, where the contour graph is indicating the orbitals, and I'm trying to, this little figure off to the left is trying to indicate what I'm showing. So this is a volume slice of the par charge from VMD. So you see that we have this slice running through the model. And assuming I did it correctly, that should be the slice we're looking at, but I'm not 100% sure I positioned it correctly in VMD. So this is just a snapshot. It actually creates a video. And this was one of my more early attempts. So it has a bit of oddities going on. As you can see, that it appears that the contour graph is actually moving and covering up atoms and uncovering atoms as it goes along. So if we go to the next slide, which is also a video but does not seem to want to play, we can see a little nicer looking one where we have the orbitals moving and the atoms, you can see them the entire time, and you can see that the orbitals seem to be playing around the lead positions. At least what I believe in the lead positions.
How do you interpret charge transfer in this video?
So video, as the video plays, it's time moving. So you can see that we have the charge. This probably is, but I don't know if you can see that the charge is changing here as time goes on. It's going from yellow now to background to blue. And you can see that happening throughout. So the idea is, with this model, we're hoping for charge transfer along basically this column of atoms right here, and with a small amount over on this one. That is the last slide.
Okay, please join me. Thank you, David. So this impressive talk can make everyone speechless, but maybe there are questions.
Sure.
I have another question. So, may I?
Yes, please go ahead.
Yeah, for different initial excitation, we need to repeat that code. So how, in addition to visualization, how we can quantify the charge transfer or other excited state parameters? How we can report that for a paper or something like that? For instance, if you repeat 3 times, we cannot put a movie inside a paper. So how we can report these kinds of results?
So this would be an addition to our standard graphs. In addition, you actually can put videos and supporting information or supplemental information.
Yes, but this could be your main results for such that study, right? Could be pretty expensive.
If you're trying to use this specifically, you would have to use a series of frames. So like this frame, and then this frame, this, then this, then this, then this, and then this. If you wanted to do this specifically in a paper, you would probably have to do a series of frames instead of a video.
Okay.
That was the main result from it.
Why do you need to specify the atomic bounds?
Because that's how they're drawn. So This one. So if you look, this line right here, that's actually specifying the distance, a cutoff distance, and this part right here is specifying to, if it's within that cutoff distance, to plot the bond. So it plots a vector.
Okay, so you're just artificially connecting them.
Yeah, we're just artificially.
In some sort, this script replaces EMD or GMO just at a little lower level, because when we need to merge this dynamics of charge with atomistic models, when needs lines depending on the distance.
You are changing the 2D plane towards and away from the atom clusters.
You mean?
You are creating that model in the 2D plane. You are moving that plane towards and away from the atoms.
So the plane should be constant about where this orange plane is in the model to the left. My understanding of how it works.
So what is the condition of changing that charge density from right to left?
So it'd be,
This is due to spatial position of your 2D plane or the
so we have our 3D model, and we have a slice somewhere through the center somewhere. So blue would be on one side of the slice, yellow would be on the other side of the slice.
So yellow, when you make the yellow, it's close to the atom clusters.
It'd be closer to the screen, to the viewer, so it's coming in and out of the screen type of idea, I think.
I'm interpreting the question of the issue a little bit different. Can you go to the slide where you create went down 2D? Okay, so I'm requesting the way it was. So here one takes the three-dimensional charge density as it has been read into script. Select at which value of a certain coordinate you want to make a slice, because plane is just fixing one coordinate and letting others change, and then calling it to the 2D order. But if one wants to redo two-dimensional dynamics at other slice of this plotting, one needs to change this parameter and do everything. So it's only one slice out of three-dimensional dynamics. And one can find different results for different ways of chopping the model. Were you asking this?
Yes. So which one we need to choose based?
Well, it's not a question to a program, but it's a question of to the one which generates results. Depending on what you need, you select position of your plane. So, okay.
Why do you need a lockpot?
So the lockpot, that's because of how Landon wrote the script. It was designed for lockpots, not for bar charges originally. And we just carried it over. So the way it works is this. So if you look at the script that we generate, the bar charge files, the last line of it is literally just copying the last one to lockpot.trim. So they have the same format. So all that's doing is reading in this first line, this 378, 120, 240 line. All that lockpot line in the code is doing is reading that in and determining what dim event is.
So it's just
because of header.
Yeah.
It's like inherited from historically. So I don't remember, like 3, 4, 5 years ago, London was undergraduate, which is not a wonder. And he was taking physical chemistry course that you guys have today. And there was a project to look for wave function and wave packet propagation in a multidimensional potential. And London decided to extract potential from ab initio data. And potential investments in the firewall code he needed to just read and put. And then several generations of researchers found this core code useful. Like there are David, maybe a few more later. There was a question from Aaron in the chat line.
Aaron asks, what if parcharts file has non-numeric values such as a bunch of stars? The best way to do this is to hope that it doesn't. Unfortunately, I wasn't that lucky. So at this point, what I've done is copy the previous parcharge to make it work. I need to sit down and regenerate them and figure out how to actually make them where they give me numeric values. And I don't know how to do that because I'm not entirely sure what causes them to not have numeric values.
Aaron, are you satisfied, or you want to give other way to avoid this problem?
Well, I'm not sure how to avoid it, but if it does happen, like generally what I do is it's 2 steps. So first, there's a Unix command to tell it to search a file for any commands. So if you just tell it to search for stars, and then you can put in another command to tell you which line that those stars are at. Then you can there's like another Unix command where you can jump to that line and just set it to 0.
Okay, so if one point out of a million has a spike or error, and we place it to 0, it will be not a big error in the integrated result.
Right. And you'll know if it's there because
I don't
like
know.
MATLAB won't load the file. It'll give an error.
Yeah, it gives a very annoying error.
And to replace is like SED or
there's a few different versions that you can do to replace this. The grep minus capital FN allows you to search for it, and gives you the line number. So the F allows you to search for the string, and the N gives you line number. That's what the FN option does.
I do have a question. Can you go to the very last slide? So I think Amir was asking about the interpretation of this results, right?
Yeah. If I think it was as well.
Yes.
So I will try to interpret, but David, please correct me. So this model consists of 3 units. So here are the fragments of thin film, which is as thin as 2 atomic layers, and it interfaces with thin film, which is as thick as 5 atomic layers. And this thin film with 2 layers and 5 layers do have different regime of quantum confinement. The gap in thinner is bigger than in thicker. So it is expected that both electron and hole will migrate from more confined to less confined. And if we try to rerun the dynamics, we will see that charge density disappears in this lower segment and will reappear in the upper segment, at least qualitatively. I mean, does it make sense just as an attempt to interpret?
Yes, of course. Thank you.
More questions, David?
I have one more question. Yeah, can you go to slide number 11, I think? So here, that red rectangular, it's for setting of XZ, right?
That's ZY.
Z. What if you want to change to another plane? For instance, if you want to change to XY plane, how do you change it?
So the Z should be the last one, and whether X or Y should be first depends on how you organize these ones.
Okay.
Depend on how you organize these ones.
I see. Okay. Okay, guys. Thank you.
There was a question in the room by Joseph.
Can I answer my question? My question was just going to be how we change the numbers for loading the atomic coordinates. But you kind of answered it.
So the idea is you got 2 dimensions, so you want, and we're looking at it in 2 dimensions. So the X and the Y, assuming Z is coming out of you on this movie again. So let's assume this is Y, this is X, and then Z is coming out. That this first row, that's going to be the X, the second row is going to be the Y, and this third row is going to be the Z. So you need to adjust them based on what your specific system is. So if you want the Z to be the X-axis in the final movie, it should be the first one. If you want X to be the first X-axis, it should be the first one. And X is the 1, 2 is Y, 3 is Z within your molecular system. So if you look at your model and it has a coordinate, those are how they relate.